All right, everybody. I'm going to be teaching you today about something called expected value. Expected value, a lot of people use this concept in Las Vegas. Let me kind of walk you through what expected value is. Let's say here is a gambling game. You walk up, somebody walks up to the gambling game. It could be a card game, it could be any type of game. And let's say they have $100 with them. And whatever this game is, they can win a lot more than $100, but they can also lose their $100. And let's say you get one try, whatever this game is, you get one chance at this game. Now, let's say it's like there's marbles in here, and if you pull out a blue marble, you're gonna get $100. If you pull out a red marble, you're going to get $20. If you pull out any other color marble, you're going to not get anything. So they do a calculation in their head. They say, all right, I have $100. I'm going to take the probability of me winning money on this game and see if it's worth me putting in $100. So they do the probability of how much you're supposed to get. They calculate it with how much money you're putting in. And if it comes out as a positive number, meaning if this is going to come out, they do the calculation in their head for them to win just one time, then the expected value is going to be better than their $100. Meaning they're supposed to win something if they do the calculation and it comes out more than $100. If it doesn't come out more than $100, let's say they have $100 and then they do the calculation of winning at this game one time, they should win at least $75. Well, it doesn't mean they're going to win $75. They can win a lot more than $75, but the fact that they're not expected to win at least $100 by playing this game one time tells them that they should not play this game. That's called the expected value. That's kind of broken down very simply. Now, in your notes, I go through a couple different things, and I go through, first thing, the expected value. It tells you what your expected value is per outcome. Outcome is every single time you play a game once. That's called an outcome. You play it twice, another outcome has happened. You play it 3 times, another outcome has happened. This probably won't make any sense until I go into a little more detail with this. Now, the way this is done, if you look at the second thing on your notes, it says you take the probability of event A happening times the amount. And the amount is usually associated with the money. Plus the probability of event B happening times your amount. Plus all the way to the probability of whatever event, however many times you do it, times however much money you paid. You add all of these together and it's going to give you one number. This number is called your expected value. If this number makes sense with the situation, then it's going to tell you whether you should play this game or not. All right, so let me walk you through this. I'm going to start off with the second example, with the money amount. I'm going to skip the coin example. I don't like that one in your notes, but I'm going to go with the money amount. And I'm going to leave this here to illustrate how this is done. So let's say there's $20, $10, there's 3 $5. So here's the amount of money. You're going to put it in a bag. $20, $10. You have $5 3 times. And then you have 6 $1 bills. One, two, three, 4, 5. Okay, so you can see here's in money. So you put all this money in a bag. Now, the expected value is going to tell you how much money you should pull out if you were to randomly reach your hand in the bag and pull out a value. Pull out a dollar bill, or not a dollar bill, but a money amount. You're gonna pull out one bill, how much that is, how much you should expect to pull out. So let me explain this with this formula that I'm gonna kind of wrap it up to make it make sense. So what's the probability that you pull out a $20 bill? Okay, well, how many $20 bills are in here? Well, let's look how many bills are in here total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 bills in here. Okay? So what's the probability of you pulling out a $20 bill? There's one $20 bill out of 11 times how much money will you win if you pull out that one bill? $20. You'll win $20. The probability of event A times the amount that's associated with that event. Okay? Plus, let's pull out a $10 bill. How many $10 bills are in here? There's one out of 11. There's only one $10 bill out of 11 bills. If you pull out a $10 bill, how much money are you supposed to win? $10, right? That's the probability of event B happening. What's the probability that they pull out a $5 bill? I have 1, 2, 3. I have 3 $5 bills out of 11 random bills in this bag. If I pull out one of these 3 bills, I'm going to win $5. Plus, and then the last one, I have 1, 2, 3, 4, 5, 6. I have 6 $1 bills out of 11 bills in this bag. And if I pull out a $6, I'm going to win. If I pull out one of these 6 bills, I'm only going to win $1. Now, watch here. 6 plus 3 plus 1 plus 1 is 11. So all of these fractions, this, and this, have to add up together to the whole game, the whole event, because there's only one $20 bill, there's only one $10 bill, there's 3 $5 bills, and there's 6 $1 bills. All of these bills together equal the 11. Now the question is, how much money am I supposed to win if I randomly reach in a bag and pull it out? How much money am I supposed to win? And all you do is this. You just do these calculations individually. So I have a calculator, and I'm going to plug the whole thing into my calculator. I'm going to go 1 divided by 11 times 20. And I'm just going to keep it simple, and I'll round to the 100th. I got 1.82 plus 1 over 11 times 10. And this is going to equal 0.91. I'm going to find the answer for this. 3 over 11 times 5, which is going to give me 1.36. Plus, I'm going to do 6 over 11 times 1 is the same thing as just whatever it was. 0.55. Now look, I'm going to add probability of point A, or probability of A times the amount, plus, which is this, plus add the probability of event B times the amount, plus a probability of I'm going to add all of these together. So I'm going to add 1.82 plus 0.91 plus 1.36 plus 0.55. And I get an answer of $4.64. That's my expected value. Now what I'm going to do, I'm going to get rid of a lot of this stuff. If I lost you, just go back right now over the steps that I did. It's super easy formula. It just looks confusing because you take the probability of each event times the amount of money. You add together all of those at the end to get an answer, but you have to relate the answer to make it make sense to you. So let's say this. Let's say you are going to play a game. Here's a bag. I'm going to throw a $20 bill in here. I'm going to throw a $10 bill in here. I'm going to throw 3 5s, and you're watching me do this, so you know that I'm not cheating. And I'm going to throw 6 1s. 1, 2, 3, 4, 5, 6. So all of these bills, boop, are in this bag. Okay? Now, I'm going to charge you money to pick out a bill. You have to pay me $4.50 to pick out a bill in here. Is this worth it? Well, remember the example that I said? Guy comes to a table, looks at the table, and he says, okay, the person at the table says, here's a bag, and this bag has all of these numbers in it, and I'm going to charge you $4.50 to pick one item, one bill from this bag. You can win $20. You can win $10. I mean, heck, you could even win $5, but you could lose your $4.50 by only winning $1, so you lose $3.50. Is this game worth it? Okay, well, what you got to do is this. Remember I told you, him thinking. I'm going to get rid of this because all of these bills are in this bag right now. So he does the expected value. He does the calculation that I told you in the very beginning in his head because he's super smart. Let's say he does the calculation with all these bills. He's expected to win at least $4.64. Now, this is impossible because he can only win a 1, a 5, a 10, or a 20. But mathematically, he's supposed to win $4.64. So if he has to pay $4.50, that means that if you go back to the beginning of the notes, I said, as long as this answer is a positive number, answer is 0.14. Now, the 0.14 is kind of irrelevant. But all you need to know is if it comes out as a positive answer, then he should play this game because he's supposed to win more money than it's going to cost him to play. If your answer came out as a negative amount, that means he's supposed to lose money. That means the money that he's supposed to lose is actually, the money that he's supposed to win is going to be less than the money it's costing him to play. So going back through this, the fact that this comes out as a positive number, he goes, yeah, all right, I know I'm supposed to win $4.64. It's costing me less money to play this game. I'm supposed to win more than what I'm going to play. So yes, I should win. This is called the expected value. That whole concept is kind of a weird concept. It's called the expected value. Now what I'm going to do, I have another example on your notes. The notes that I have for you is the second example where it says the world famous gambler from Pennsylvania, Senor Rick, proposes the following game of chance. You roll a fair die. The reason why it's called a fair die is it's not weighted. It's just a normal dice. So you can get a 1, a 2, a 3, a 4, or 5, or a 6. What's the probability of you getting a 1? 1 out of 6. What's the probability of you getting a 2? 1 out of 6. What's the probability of you rolling a 3 on a dice? You should understand it's 1 out of 6 every single time. Okay, if you roll a 1, then this Senior Rick pays you $25. If you roll a 2, he pays you $5. Let me do this. This is how much money is associated with each thing. If you roll a 3, you win nothing. So you win $0. If you roll a 4 or a 5, you must pay Senior Rick $10. So you owe a negative $10. If you're paying somebody, it represents a negative. If you roll a 6, you must pay Senior Rick $15. Should you play this game? Remember that example that I told you? Here's a table. Here's some guy comes up. Here's Senior Rick. He says, hey, play this game. Here is a set of dice. I don't know, 1 and 2 and 3, 4, whatever. Here's your set of dice. He says, here's the rules. If you roll a 1, I'm going to give you $25. If you roll a 2, you're going to get, I'm still going to pay you $5. If you roll a 3, you ain't going to get anything. But if you roll a 4, 5, or 6, you're going to have to owe me money. So he thinks about, he's not paying any money to play this, but he goes through and looks at, what is my expected value? How much, if I play this game, is this game worth playing? What is my expected value? How much money am I supposed to win, or am I supposed to lose money? The calculation that he does is this in his head. So what I'm going to do is this. I'm going to do this calculation, each one of these. If you have a graphing calculator or a calculator like this, you can just plug everything into your calculator and it'll spit you out the answer if you know how to like put parentheses around everything. But just for the sake of explaining this, I'm just going to go through this individually the whole way. All right, so I'm going to go 1 divided by 6, press equals, times 25. And I'm going to round to the 10th, or to the 100th, 4.17. 1 divided by 6 times 5. I get 0.83. This is going to, anything times 0 is 0. 1 divided by 6 times negative 10 is going to give me negative 1.67. This is also going to give me negative 1.67 because this is the exact same as this. And last one, this one, 1 divided by 6 times negative 15 is going to give me negative 2.5. So he's still doing all these calculations. And Senior Rick saying, hurry up, fool. We got to figure out you want to play it or not. And this fool saying, yeah, let me do the calculation in my head. Or he has a calculator. Let's say, because he's not playing it yet, so he pulls out his calculator. He's like, hold on, dude. Let me do this calculation. Gets out a piece of paper. He goes over the rules, does this expected value. How much is what's the expected value of this game? So I'm going to add all these numbers. This plus this plus this plus this plus this plus this. All right. So I have negative, I'll just go from the bottom up. Negative 2.5 plus negative 1.67 plus a negative 1.67 plus 0 plus 0.83 plus 4.17. And he gets a value, his expected value of this game is approximately negative 0.84. So he's thinking, should I play this game? Well, if he plays this game, he's expected to lose 84 cents. That's impossible because he only has to, you can only win $25, win $5, nothing, or lose $10 or lose $15. You can't lose 84 cents. But it's the concept of expected value. Meaning if he plays this game, if this was any positive number, that means he's supposed to win something. Yes, he should play this. If he plays this game and he gets a negative answer as an answer, that means he's supposed to lose money. He's supposed to lose 84 cents. That's impossible because he can only win or lose this amount of money from the example. But the concept is he's supposed to lose 84 cents. So he says, nope, I ain't going to play that. Mathematically, the probability of me winning does not work out in my favor. But let's say he did do this, and the answer was a positive 84 cents with all this information. It's not, but let's just say it was. That means if he plays this game, he's supposed to win 84 cents. It's impossible because you can only win 25 bucks, $5, nothing, or lose 10 bucks or lose 15 bucks. But if the answer was positive 0.84, that means he is supposed to win a positive amount of number. The positive amount of number, if he's not putting any money down to play, is irrelevant. The fact that he comes out positive means, yes, he should play this game. But this calculation gave him a negative answer. He's going to tell Senior Rick, nope, tripping fool, I ain't playing that game. And he walks away. This answer is called your expected value. And if you're playing money to play this game, you have to subtract this answer from the amount of money you're playing to see if you still come out in the positive. And that simple concept is called expected value.